Is there an effect in blocking thermal kinetic energy from the outside in the case of a metal compound that is a mixture of multiple components rather than a single component metal? A mixture of multiple components in a metallic compound has the ability to impede the transfer of thermal energy from external sources. This is due to the fact that the lattice structure of metallic compounds is more complex and irregular compared to that of single-component metals. The complexity and irregularity of the lattice structure make it difficult for thermal energy to propagate, resulting in a reduction in thermal conductivity. For instance, the thermal conductivity of a single-component metal like silver is 429 with mK, whereas the thermal conductivity of a metallic compound like copper is 385 with mK. This is because the lattice structure of copper is more intricate and irregular compared to that of silver. Therefore, for applications where heat blocking is required, metallic compounds with multiple components are more effective than single-component metals. For example, the body of a train or the inner walls of a refrigerator use metallic compounds with low thermal conductivity to block heat and maintain the internal temperature. However, the thermal conductivity of metallic compounds can vary depending on the type of metals and their mixing ratios. Therefore, to select the appropriate metallic compound for a specific application, these factors need to be taken into consideration. So, is there a possibility of a method that can maintain the effect of blocking thermal kinetic energy from the outside while promoting the movement of electrons within the metal itself through an appropriate combination of various metal and non-metallic components? There is a possibility of achieving a method to promote the movement of electrons within the metal itself while maintaining a barrier effect against thermal energy from external sources through an appropriate combination of various metal and non-metal components. To achieve this, two main considerations need to be taken into account. Firstly, the lattice structure of the metal compound should be made complex and irregular. This is because it hinders the movement of thermal energy. Secondly, the electrical conductivity of the metal compound should be enhanced. This promotes the movement of electrons within the metal itself. To satisfy both of these factors, it is essential to carefully combine metal and non-metal components. For example, when metallic and non-metallic atoms are bonded to form high-conductivity semiconductors, mixing these semiconductors with metals can reduce the thermal conductivity of the metal compound while enhancing its electrical conductivity. Additionally, when metallic and non-metallic atoms are bonded to create polymers, incorporating these polymers with metals can introduce complexity and irregularity into the lattice structure of the metal compound. By employing such methods, it is anticipated that metal compounds can be developed that actively facilitate electron movement within the metal while maintaining the barrier effect against thermal energy from external sources. The possibilities include utilizing metal-non-metal composites. Combining metals and non-metals forms composites with characteristics of both components, allowing for enhanced electron mobility while still maintaining the thermal insulation effect. For example, the combination of metal-nickel and non-metal selenium results in a nickel-selenium composite with low thermal conductivity and high electrical conductivity, suitable for transmitting electrical signals while blocking heat. Using metal nanoparticles. Metal nanoparticles retain the properties of metals, but due to their small size, they can impede the movement of thermal energy. Therefore, properly dispersing metal nanoparticles can lower thermal conductivity while keeping electron mobility high. For example, dispersing copper nanoparticles effectively reduces thermal conductivity while maintaining electrical conductivity. Employing metal polymer composite materials. Combining metals with polymers creates materials that possess both the strength of metals and the flexibility of polymers. Thus, selecting the right metal polymer composite can ensure active electron movement and thermal barrier effects. For instance, aluminum polymer composites combine low thermal conductivity with high electrical conductivity, suitable for transmitting electrical signals while blocking heat. While these methods are still in the early stages of research, there is potential for their application in various fields in the future. The thermal conductivity of metals involves the simultaneous movement of electrons and thermal energy, and finding a method to enhance electron mobility while blocking the transfer of thermal energy can help maintain both the intrinsic electrical conductivity and thermal barrier effects of the metal. To achieve this, several methods can be considered. Finding the right mixture ratio of metals and non-metals. Properly mixing metals and non-metals can lower thermal conductivity while preserving the electrical conductivity of the metal. For example, mixing silver and germanium can result in a metal compound that maintains silver's electrical conductivity while reducing thermal conductivity. Altering the lattice structure of metals. Changing the lattice structure of metals can hinder the movement of thermal energy, thus reducing thermal conductivity. For instance, adding carbon to silver alters its lattice structure and lowers its thermal conductivity. Coating the metal surfaces. Applying a coating to metal surfaces can prevent the transfer of thermal energy into the metal. For example, coating aluminum surfaces with graphene can reduce aluminum's thermal conductivity. Through these methods, it is expected that metal compounds or coatings can be developed to maintain both electrical conductivity and thermal barrier effects. Research in this area is currently active, with some successful results. For instance, a South Korean research team has developed a metal compound that combines silver and germanium to achieve low thermal conductivity while maintaining high electrical conductivity. Additionally, a U.S. research team has successfully reduced thermal conductivity by coating aluminum surfaces with graphene nanoparticles. If such research continues to advance, metal materials with combined thermal conductivity and thermal barrier effects could be developed and utilized in various fields.